Welcome to Let's Get to the Marks, going through the AQA AS Chemistry Paper 2. This is the Organic Chem Physical paper. It's an hour and a half. It's the 2024 paper. There's 7 questions and then the multiple choice section B. Don't forget to grab a pen, grab a bit of paper, make the revision active. So as I go through the questions, pause the video at the start, have a go at the question, and then unpause to watch the rest of the walkthrough. All right, let's get into it. Question 1. This question is about the analysis of organic compounds. 1.1. Table 1 shows the results of chemical tests on 3 organic compounds. Complete the empty boxes in the table. So we've got the name of the chemical test, but one is missing. And then we have on the rows the results of the chemical test. We also have the structure of 3 different compounds. And from that, you should be able to work out what the missing areas are in the boxes. It's worth 3 marks. Let's have a little look. Okay, so all we need to do is complete this table. So for the first row, we have a chemical test and they've added bromine water to each of these 3 compounds. What would be the result? Well, with the first one, we're told it's orange to colorless, and that's because it has a double bond. So the bromine is adding across the double bond. We can see here there is no double bond. There's no carbon-carbon double bond. We do have a carbonyl bond. We have this bond. Bromine can't add across that bond. Bromine can only add across the carbon-carbon double bond. So this is going to remain orange, or you could say no visible change, or we could say remains orange. There we go. Let's go and look, and that will get you 1 mark. Let's have a look at the others. Okay, for the second row, it says the name of the chemical test. So something has been added to each of these 3 structures. We can see we've got an alkene. You should be able to recognize the functional group of the second structure. It's a carboxylic acid. And then over here, we have a ketone. So what is added? There was no change with the alkene, bubbles of gas with the carboxylic acid, and with the ketone, no change. So essentially, we're looking at something that's been added that identifies acids. And in organic chemistry, that's going to be a carbonate. So we could say something like sodium carbonate. It doesn't really matter which carbonate you pick. I'm going for sodium carbonate. That would bubble because it would release carbon dioxide. You can test for that with lime water, which would go cloudy, and that would react with carboxylic acids just like it would react with hydrochloric acid or sulfuric acid. Maybe not quite as vigorously, but it would still react with them. Okay, let's look at the third row. So we're going to warm each one of these structures with failing solutions. So when warm with the alkene, we get no visible change. When warm with the carboxylic acid, we get no visible change. Now, do we get a visible change with this? Well, this is a ketone. With an aldehyde, we would get a red precipitate, but with a ketone, it cannot be oxidized further. It can't be oxidized to a carboxylic acid. Only aldehydes can, and aldehydes are at the end of the chain, just like carboxylic acid. So this ketone can't be oxidized further. So we should write no visible change. It's going to remain blue. So they might give you the marks for saying remains blue. So I'm just going to put no visible change, as that's what they've written with all the others. And that's your 3rd mark. Lovely jubbly. Right, we're going to move on to question 1.2. So 1.2, 0.500 grams of a hydrocarbon is analyzed. The hydrocarbon contains 0.450 grams of carbon. Calculate the empirical formula of this hydrocarbon. It's worth 3 marks. Grab your calculator, grab your pen, give it a go, and then I'll go through the answers. Okay, here I'm going to go through the answers. So first of all, we know this thing is a hydrocarbon. Go back to your GCSE. That is a compound containing only carbon and hydrogen. As we've been told, it has 0.450 grams of carbon and 0.50 grams is the total. We can work out how much hydrogen is there. So we go 0.500 and we minus 0.450, and we now know how much hydrogen there is. So if you can't do that in your head, just stick that in the calculator, like me, because I'm a dozo when it comes to doing these. And we're going to end up with 0.05 grams of hydrogen. So now we know the answer. We can work out the empirical formula. That's the carbon, that's the hydrogen. So you go ahead and work it out as if it's moles. Now, this should get you the 1st mark. And then we want to go ahead and work this out like it's a mole equation. So we're going to go 0.450 for the carbon. We're going to look up the atomic number of carbon, sorry, the mass number of carbon. We don't use the atomic number for moles. And of course, it's mass over mR gives you moles. So we're going to do 0.450, sorry, divided by 12. And that is going to give me 0 0.0375, and that's like my moles. If this was percentage by mass, you just pretend the percentage is grams. So you do it the same way, even though you're not really working out the moles. And now I've got 0.05 grams of hydrogen. We're going to divide that by 1, and that's going to give me 0.05. Yikes, I want a little n there for moles. So that's going to be my second mark for working out this and this. Now what I want to do is I want to divide both by the smallest so I can get these. I need to get these into whole numbers. Let's divide them both by the smallest. The annoying thing is I put a tick right there where I need to do the dividing. So let me remove the tick. That's maybe the second mark. Maybe the second mark is actually this. So anyway, the smallest number is 0.0375. So we're going to divide them both by 0.0375. That dot was a bit crusty. And what we're going to get here, that is going to be equal to 1. And this is equal to like 1.33 recurring. I now go, damn, I can't write 1.3 in an empirical formula. I need a whole number. What can I times them both to get them roughly to a whole number? Well, if I times both of these bad boys by 3, I'm going to end up with carbon as 3 and hydrogen as like 3.99, but we're going to round that up to C3. H4, and that is your empirical formula. So there we go. Lovely jubbly. All right, guys, don't forget to hit the like, sharing's caring, punch up the bell, subscribe. You know the coup. I'll see you on the next one. Okay, I'm going on to question 2. Let's have a little looky at question 2. So this is question 2. This question is about infrared spectroscopy. 2.1 compounds A and B both have the molecular formula C4H8O2. Figure 1 shows the infrared spectra. Where are we? Yeah, the infrared spectra, lost myself there, of compounds A and B. So here we go. We've got the infrared spectra of A, we've got the infrared spectra of B. Use the infrared spectra to deduce a possible structural. Oh, I've forgotten how to speak. Use the infrared spectra to deduce a possible structure formula for the compound A and a possible structural formula for compound B. That was my, yeah, never mind, stupid voice. 2 marks. So we've got the percentage transmittance, and we've got the spectrum, we've got the wave number. Let's zing-a-ding down. Possible structure of A, possible structure of B. So let's get into this one and do that. I'm going to do this here on here so you can see how it looks. So the first thing I need to do is get me data book up. Let's find that data book. That's not my data book. Right, let me zang that. Chemistry A level data book, and we're going to go PMT Bosch. There we go. Loving it. Right, let's go down here. Okay, so what we're doing here, we're going to identify compound A and B just from the infrared spectra. So let's check out something else we have to know. So we've been given the formula is C4H8O2. So what we want to do is bear that in mind, and I'm going to look at the first one. So first of all, I can see there is some sort of peak right about, I don't know, what's that, 3,400, sort of around there. 3,400, there's some sort of peak. And also I've got this telling peak here. Actually, I'm scribbling all over it, which gets in the way. Let's be a little bit more accurate. There's 1,500, there's 16, there's 17, right? It's above 1,700. And I'll show you why that's important, right? That's like 17, it might be like 1725. Okay, let's go to the data book and see what things we can come up with for that. So bear with me, peeps, as we check this out. Okay, here's the AQA datasheet. So what I want to examine here, guys, is we had one about 3,400. That looks like it is some sort of alcohol bond. Nice. So it looks like we've got an alcohol. Is it a carboxylic acid? No, the OH bond on the carboxylic acid would be before 3,400. So ours is likely to be the alcohol. We could ask ourselves, is it the amine? But do you remember the formula they gave us? The formula was C4H8O2. There was no nitrogen, so it's not going to be an NH bond. So we're pretty sure it has an OH for alcohols. Now, what about the 1725? Well, that looks like it's a the carbonyl bond here, the C double bond O. Why can't it be the alkene bond? Well, because that peak would have been before 1700, and you'll probably remember ours wasn't. So I'm really going for this bond and this bond. Let's go back, smash that on, and see if we can come up with a structure for that. Okay, here we go, guys. So what I want to do is, huh? No. Okay. That went a bit pear-shaped, didn't it? Right. So what I want to do here is just notice once again that is round about 1725. That was round about 3400. This told me that this is a alcohol. That's for alcohols, not acids. So that's the alcohol. And this is that carbonyl bond. So we could have an aldehyde or a ketone here, but not a carboxylic acid. Otherwise, we'd have got a broad peak around. We'd have got a broad peak around just before 3000. Okay, let's get into it. The formula is C4H8O2. So what I want to do is try and come up with the structure. So I'm just going to put like butane, right? Let's do 4 carbons in a row. Bute, we got that. We got H8 and we got O's. Let's stick in an alcohol and see what happens, eh? So I'm going to put an OH coming off the first carbon. Let's work on that. Let's put a bond there. I always forget to do that. That's kind of important. They could take a mark off of that if you're doing displayed formula. Did they want skeletal? No. No, I think we can do displayed, so we're all right. I need to do all the hydrogens because we need to add them up and see that we have enough. I need to stick a double bond in here. Now, let's try, if I try it like aldehyde, let's see. So this is an aldehyde. Let's count up the hydrogens here. 1, 2, 3, 4, 5, 6, 7, 8. So that works, but let's see if the ketone works as well. So let's bust out a ketone. If I smash the ketone in, bosh. Well, that works, doesn't it? So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go with that. To me, either one of those is good. Doesn't matter, but that fits the formula. We've got 4 carbons, 8 hydrogens, 2 oxygens. Boom, 2 marks. Oh, it's 1 mark. Sorry, 2 marks for both of them. Right, let's get on and do structure B. All right. So let's check out structure B. Here's structure B. Once again, got another peak here. That's looking like an OH once again, pretty identical to that there. So we're looking at OH again, alcohol. What else? What else? What else? What else? We've got. Hmm. I can't really see anything else of significance. There's no carbonyl around here. So I can't really see anything else of uber duper significance. This is just really the fingerprint region, which is a way to identify, like you've got a fingerprint region here where they're all very close together. Each substance has its own unique fingerprint. It's one way to identify um, when you have isomers with the same molecular formula, you can use the fingerprint region if you're lucky enough to have a data book to compare it to. Okay, we're going alcohol here, but that presents a problem because I've got 2 O's. So what I'm going to do, I want a diol. So I'm going to do like butan and then stick 2 OHs in and see if that works it for me. Okay, let's do uh, struggling. Oh my gosh, I think that is far too many H's. That does not work. Let's go 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's got 2 O's. Hold on. 1, 2, 3, 4, 5. What have I done here? Um, 6, 7, 8, 9 H's. I don't think that's working. I probably need to have a little think about the structure here. Um, okay. Maybe we've got something else here. Let's go and check out if there is something else there. Let's go to the data book and have a little look. Okay, what have we got? What have we got? Ooh, have a look here, folks. Double bond at 1620 to 1680. That's going to help me out with getting rid of one of those hydrogens because I've got 9 hydrogens at the moment. Let me go back and stick a double bond. Oh my gosh, my formula's disappeared. Right, let's stick a double bond in there. So what do we have? We had C4H8O2. Let's do that again. But this time we're going to smash a double bond in. I'm going to smash one there. Um, and then let's put the hydrogens on. Oh, and I want 2 OHs. I'm going to stick 1 OH there. Let's put another OH there. Doesn't really matter where they go. There definitely isn't anything else with an O in coming up on the data book other than that OH bond in alcohols there, but it looks like I got the double bond there. So let's smash all of these in. Let's see. Does that give me the right number? You've got to check with your carbons that you've got four lines around each because it's in group four, four electrons, four lines. So let's have a look. H, that's three H's, four H's, five H's, six H's, seven H's, eight H's, one, two, three, four, one, two, three, four. Always check around the double bond that you've got four around each. So that is my other possible structure, and that's going to get me 2 marks. So we've got the double bond. Lovely. That's going to get me 1 mark. Sorry, we get 1 mark for the compound A. This is compound B. Awesome. Right. That took long enough. It took about 12 minutes for 2 marks there. Never mind. Okay, let's zing. 2.2 shows the infrared spectrum of either pent-1-ene or 2-methyl-butene. So, nice. Outline how to use the infrared spectrum to determine whether the compound is pent-1-ene or 2-methyl-butene. We have a problem here, folks, and that is that pent-1-ene's functional group is that, and pent-butene's functional group is that, which means they both contain that double bond there, okay? So what we have to do here to distinguish between these, because there's everything else is just carbon and hydrogen bonds, so everything else is CH bonds. So there's not going to be a big difference in the functional groups. Well, no difference because they've just got this and this. But what we can look for in any compound is its unique fingerprint region. So 2-methyl-butene will have a different fingerprint region to pent-1-ene. So what I'm going to say is um, use the fingerprint region, compare to known data book of different fingerprint regions to identify the compound. So basically, we just need to go to the data book, and there'll be a data book with a fingerprint region for 2-methyl-butene and one for pent-1-ene, and we need to use that to identify it. We can't actually use it by looking at the peaks where the functional groups are because they contain the exact same functional groups and the same amount of everything. Okay, super, super, super. So fingerprint region and compare to a data book. It's going to get you the 2 marks. Why I put 3 ticks is beyond me. Oh my gosh, the question doesn't stop giving it with the infrared. 2.3, figure 3 shows the infrared spectrum of methane, percentage transmittance, and then we've got the wave number at the bottom. Use the information to explain why methane acts as a greenhouse gas. So all we need to do is point out, let's go to that, let's go to the data book. Now, we know that methane, right, contains so I'm at the data book here, guys. Methane, what bonds are in methane? It's only got CH bonds. So our answer is going to have to be something along about these CH bonds. So what is the CH bond? The CH bond is found at 2,850 to 3,300. So let's go back and try and put some sort of answer together. So over here, we can see, yep, there is CH bonds around 3,000, sort of, yeah, between that number. I've forgotten what number that was. So there are CH bonds at 3,000 wave number that absorb infrared radiation. So for you to be a greenhouse gas, you've got to absorb infrared radiation. And yeah, you've got to be able to absorb IR. And it's that carbon hydrogen bond that does. So that is going to get us the mark. Carbon hydrogen bonds at 3,000 absorb the infrared radiation. Lovely jubbly. And that's the end of the question. Don't forget, sharing's caring, hit the like, punch up the bell, subscribe. Let's get to the marks. Okay, we're going to go on. What are we going on to? We're going on to question 3. Okay, whoa, what happened to the rest of the question? I went a bit trigger happy there. Okay, we got question 3. This question is about CFCl3. So CFCl3 used to be the propellant in most aerosol cans. That's probably up to the 1980s. Use the IUPAC rules to name CFCl3. So let's get into that. It's a carbon. It's got an F attached and it's got 3 chlorines attached like so. Nice. So how are we going to name this? Well, it's a methane, isn't it? It's got 1 carbon, so we know it's methane. Um, but it's got no hydrogens attached. It's got three chlorines and a fluorine. Now, alphabetically, what comes first, fluorine or chlorine? Well, it's going to be the chlorine that comes first. Now, do I need to number the carbons? No. So I don't need to go 111 trichloro. I can just go trichloro because there's only one carbon in it. So this is going to be trichloro. Fluoro. We don't need to number it and say one fluoro because it's just one fluoro. And then it's methane, which is not spelt like that, is spelt like that. So it's trichlorofluoromethane. Lovely bubbly. And that will get us a mark. Okay, let's go to 3.2. Give an equation for each of the two propagation steps in the conversion of CHFCl2 into CFCl3. So we want to make this, but we want to make this from CHFCl2. How do we go from that into that? And it's saying this happens in two propagation steps. Now, a propagation step, something that you need to learn off by heart about propagation steps, um, they involve a radical, free radical, but I ain't got the rooms and I can't spell involve. I've said invol. Yeah, anyway, they involve a radical in the reactants and products. So that's a useful thing to know, that the propagation step will have a free radical in the reactants and products each time. So you know you're going wrong if you haven't done that. So we know one of the reactants is CHFCl2, right? And this is going to be, what's it going to be reacting with? Well, we're trying to add another chlorine on. So we're going to bust out a chlorine free radical. But what's going to occur here is that the chlorine is going to steal this H and form HCl. And we're going to be left with CFCl2, right? Because the hydrogen's been taken off to join with that chlorine. However, this is now a free radical. This has now got the unpaired electron, and the hydrogen chloride is sorted. Now what's going to happen? Well, we need to put this back into the mix, and it's going to be another propagation step. So this is going to be important. It's a propagation step. And of course, that means that what we need to have here is this. Now, you might be tempted to go, okay, all I need to do is smash another free radical in, and that's going to give me the product they wanted, which was that CFCl3. But that is not a propagation step. That's a termination step when two free radicals come together. So what I need to do is get rid of that. I need to think to myself, what could this react with that would get it a chlorine and not be a termination? And the answer is a chlorine molecule. So if it reacts with a chlorine molecule, one of the chlorine atoms is going to go there, and we're going to get CFCl3, and that is our product that they wanted us to make. But we're also going to reform a chlorine radical that can then go on and propagate more. So those are your two answers. Like I say, you should always pause the video and have a scribble down, have a go at the questions, and then unpause and watch me explain them. Okay. 3.3, in the presence of ultraviolet radiation, CFCl3 breaks down in the upper atmosphere to form chlorine-free radicals. Give an equation for this reaction. So we want to do an equation to show the formation of the free radicals from that. So they've given us the starting point. So that's lovely, right? We've got CFCl3. What is it that causes it to break down? It's ultraviolet light. I like to write that on the arrow. And then we are going to snap this to form the free radicals. And guess what? We're going to get that, and we're going to get a chlorine free radical here. There we go. That is an initiation reaction. You get one reactant becoming two free radicals. So it's good to always know what your initiation is. And there we go. Okay. Zing, zing, zing. 3.4, chlorine-free radicals catalyze the decomposition of ozone. Give two equations that show how chlorine-free radicals decompose ozone. This is just pure subject knowledge memory recall because you need to learn these off by heart. The other ones we did earlier, you kind of have to be able to apply your knowledge of free radical mechanisms. This is just a memory recall one. So two equations, let's show how free radicals decompose ozone. So we know we've got a chlorine free radical, right? We know that's in the equation, and we know that it's going to react with ozone. It's telling us it reacts with ozone. So you know your starting point. If you haven't memorized it, they're giving you a clue. Chlorine free radical plus ozone. What's it going to make? Well, this is going to be a propagation step. Otherwise, there wouldn't be an equation two. So we're going to slam into that. And what's going to happen? We're going to get a chlorate free radical, and we're going to form some oxygen gas. And then in our second equation, propagation step, we want to take this chlorate free radical down, and we've got this chlorate free radical. And now this is going to react with a molecule of ozone. And does it stop there? Does this one chlorine free radical just cause the breakdown of two ozones? Well, maybe not. This thing can go on and break down millions, because it's going to steal that oxygen to there to make oxygen, but it's left behind. The chlorine free radical again has been reformed, and it is able to go on and break many millions more oxygen molecules before it gets terminated with another chlorine radical or something. Right, 3.5, the production should give ourselves two little ticks for that. Right, nice. 3.5, the production and use of CFCs have been banned in many countries because they decrease the amount of ozone in the upper atmosphere. State why ozone in the upper atmosphere is important for life on Earth. This is because ozone absorbs. Now, it's the harmful. Now, I don't know if you have to be specific and say UVC, because there's these UVC, A, B, whatever rays. You have to be specific. I think in the AQA syllabus, we can just say ozone absorbs harmful ultraviolet radiation. And then I'm going to explain which can cause skin cancer. Actually, it says why it's harmful to life on Earth. So I think we're just saying ozone absorbs harmful UV radiation is enough. And that is it. That's all we need to say. We don't need to specify which bit of the radiation is harmful. Is it UVA, UVB, or UVC? I don't think that's on the syllabus. So we're cool. All right, guys, don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks and smash those exams. Okay, welcome to Let's Get to the Marks. I'm going through a little question here on the Carn-Ingold Prelog rules. And why don't you grab a pen, grab a bit of paper, have a go at this question, and then unpause and watch me go through the explanation. All right, this is a chemistry A-level walkthrough. Let's go. 4.1. Compound J is one of a pair of stereoisomers. So here we have compound J. You can see it's got a double bond in the middle here. We've got a hydrogen atom there. We've got like an ethyl group coming off there. We've got a group with three carbons coming off there and another ethyl group here. Explain what stereoisomers are, how EZ stereoisomerism occurs, how the Carn-Ingold Prelog rules can be used to decide whether compound J is an E or a Z isomer. So first of all, let's deal with the first bit. What are stereoisomers? So stereoisomers have the same number and type of each element. So we could say same molecular formula, or same structural formula, but a different arrangement in space. So we're really looking at, they have a different spatial arrangement. Same elements, same type and number of each element, but they're arranged differently. Now, how does EZ stereoisomerism occur? So in order for you to have EZ stereoisomerism, actually, I'm not even going to write that, but in order for you to have EZ stereoisomerism, you need a carbon-carbon double bond. So I can say carbon-carbon double bond with different groups attached to each of the carbons in a double bond. Now, I could have shortened that down massively by just saying you need different groups attached to each carbon in a double bond. And the fact that we also want to add in there is no rotation around a double bond. So what this means, why is that important? Why is the no rotation around a double bond important? Now, I think probably these three things are only 2 marks, but the reason is, you see, I have a hydrogen here and I have an ethyl group there. If there was rotation, then this hydrogen could rotate any 1 second and be there, and then the ethyl group could be there, and then this group could rotate there, and then they could constantly be swapping and revolving and changing their structure, because at one moment you could have the hydrogen and this on the side, then you could have the hydrogen and that on the same side, then the hydrogen and that on the same side. So they could keep going. That could be on the same side with this, or that could be on the same side with that. So they would keep flipping between the EZ forms, but that's not the case. Because there is no rotation, we get two distinct forms, which are the EZ isomers. Now, what we're going to do, we're going to look at how the Carning-Gold Prelog rules can be used to decide whether J is an E or Z isomer. So the first thing to do is check the first carbon. Now I can label these carbon 1 and 2. It doesn't really matter which one I label 1 and 2, but for the purposes of explanation, it's easier for me to label them. So I could do A and B or whatever. So looking at the first carbon, so looking at first carbon, the group attached with, I don't know, let's say the lowest atomic number is given low priority, and the group with the highest atomic number is high priority. So what I'm going to do here, we can see that hydrogen has an atomic number of 1 and carbon has an atomic number of 6. Therefore, this becomes low priority, LP, and this group becomes the high priority group. So I need to put that in words. So looking at first carbon, group attached with lowest atomic number is given low priority. This is H, as has atomic number 1 compared to C, atomic number 6. Okay, I've used abbreviations because I'm running out of room. So that's just my explanation there. So I've explained what's going on there. I now need to look at the second carbon. And here we've got a little bit of a clash, because when we look at the second carbon, the groups attached, I've got 6 and I've got 6. So we have the same atomic number attached. So then we've got to go to the next set of groups attached. And this has got 2 6s attached. And this has got just 1 6 attached. So I need to put that in words. So on second carbon, top group has high priority, as has atomic number. It's basically got a 6 um, followed by kind of 6 6. Okay, it's really got 6 6 and it's got 6 1 1 1. So attached, that's 6 1 1, that's 6 1. So this one is the higher priority and this one is the lower priority. It's got 6 1 1, but then it has 6 1 1 1. So this has got a total, you could say, of 9, and this has got 6 1 1 6 1 1. That's got a total of like 18 attached when you move to the second group attached to that carbon. So we're going to give this high priority and this one low priority. So on the second carbon, top group is high priority, as has atomic number 6 followed by 6 6. Whereas the other group is 6 followed by like 6. If I want, I can say 1 1 1. But I mean, I should really say that these, I should put over here that this is 6 1 1 1 and 6 1 1 1, 6 1 1 1, and that is 6 1 1 1. And then, yikes, that's come out real messy. I kind of run out of room there. Right. So what does that mean? That means that because we have we have different groups on the same side of the double bond. So this is the double bond. When you have a low priority and a high priority on the same side, it's going to be a E isomer. E stands for antigen. So I've run out of room, so I'm going to say this is an E isomer. E stands for antigen, means opposite, and that means the high priority and low priority, you've basically, it's diagonal. It's like trans. So it's you have a low priority and high priority on the same side. So HP and LP on same side, double bond. So you've got opposite groups on the same side of the double bond. If I had low priority, it would be Zuckerman, Z isomer, which stands for sisters. Anywho, I longed that out. So yeah, we get 6 marks for that. All right. Well, let's look at this 4.2. Compound J reacts with hydrogen bromide to form compounds K and L. So we've got compounds K and compound L, and they came from J, which was this one here with a double bond. So let's zing back down. K is the major product. So this one is the major product. L is the minor product. Name and outline the mechanism for the formation of K. So we had this, which is J, and then a bromine attached. So what we've got here is we've got a double bond and we've got stuff adding across the double bond. So it is addition. So we've got nucleophilic. Is it nucleophilic addition? I think it's going to be electrophilic addition. Why electro? The double bond here is a source. Oh, couldn't highlight it. The double bond here is a rich electron or an area of rich electron density, or it's rich in electrons. So we're going to say electrophilic addition. And now that's going to get us just one mark for the mechanism naming. Now we need to draw the mechanism to show how K formed. Now we can see from this that the Br, we got the ethyl, we got the propyl, we got that carbon is the first carbon. So the Br is joining there and the hydrogen is joining there. So how does this work? Well, did it tell us? Reacts with hydrogen bromide. So we were told hydrogen bromide. So we want to do hydrogen bromide comes along like this. And of course, this is delta negative. This is delta positive. And of course, a lot of people will make the mistake and do an arrow showing that attracted to the electrons. Yes, it's attracted to that electron-rich area, but what actually happens is a pair of electrons leave that bond and go to the hydrogen. Now, hydrogen is basically a group 1 element. It has one electron in the outer shell. It can only have one covalent bond at any one time. Bromine group 7, it can only have one covalent bond at any one time. So you cannot have this bonding here and maintaining this bond. So this is going to need to go. We draw a curly arrow coming from the bond. Make sure it almost touches that bond so that the examiner is sure it's coming from the bond and not from these atoms. So this pair of electrons are coming from the bond and going to the delta negative bromine. And that's the first stage of that mechanism. Now we need to do the next stage of the mechanism. I've got to draw the carbocation, which is a pain in the butt because it means I got to draw all of this out. Right, now it's a case of where does the hydrogen grow? Well, the hydrogen will always go to the carbon atom uh, with the most hydrogens already attached. So that's this one here. So it's going to attach there. And there's a reason for that. It's because you're going to end up with a carbocation with more alkyl groups stabilizing the atom. So let's get into it. And we're going to go like this. The double bond has disappeared. So this is the kind of before and after. And then I just want to copy the rest of this out. So CH3. Oh, jeez Louise, man, that's long. Let's bust that CH3 there. Then we're doing this carbon here. Now I need CH2. And I need CH3. And we're going to put a plus sign there. And then over here, we're going to put an H. And you can tell, look, CH2, CH3, CH2, CH2. We've been told to do compound K. So you can see CH3, CH2. This CH2, that bit became that. So that's going to happen first. And so we're going to add a hydrogen to here. So we're going to go CH2, CH3, and we're going to add another hydrogen. And there's a reason why this forms, but we'll go into that later. That's not part of this. And then we're going to put the electrons, and we need to put a negative sign and then draw an arrow from there to there. So I think pretty much your marks are 1 mark for the name, 1 mark for the curly arrow from the double bond here, 1 mark for showing the polarization of this bond, 1 mark for the curly arrow from that bond to there, maybe 1 mark for the carbocation, and then you need to have the bromine needs to have the negative and the electrons on it. And there we go. That's our mechanism. Let's go down and see what the next question is on this. Explain why K is the major product. So the reason why K is the major product and L is the minor is because when this is like that, that is like that, they get a positive, well, yeah, get the idea. There's a positive charge on that carbon, and then the bromine is going to either attack that or attack that. And the reason why this intermediate, this carbocation is most likely to form is because this is a tertiary carbocation. It has three alkyl groups attached. All of these are kind of electron donating, and so they stabilize the positive charge on that carbon atom. Okay, let's go put that into words. So the carbocation that forms for K is more stable. So that's going to be a mark. Why? Because it has more alkyl groups attached. This is probably the same marking point, but it is a tertiary carbocation instead of a secondary like L. Um, Therefore, more electrons are donated to stabilize the carbocation. They're not really donated. They have like an inductive or whatever. They have an effect where they kind of electrons are donated towards that positive ion. The cloud of electrons of each of the alkyl groups moves towards that positive charge, stabilizing it. Anyhow, so anywho, carbocation is more stable. There's more alkyl groups. It's a tertiary carbocation. So there's more electrons that are donated. Yeah, three of those will get us the marks. Right, question 5. This question is about the volumes of gases involved in some reactions. 5.1. Magnesium reacts with hydrochloric acid. Magnesium solid plus 2 HCl aqueous goes to MgCl2 aqueous plus H2 gas. 0.400 grams of magnesium is added to 20 centimeter cubed of 1.5 mole per decimeter hydrochloric acid. Identify the limiting reagent. Justify your answer. Calculate the volume in meters cubed of hydrogen produced at 101 kPa and 15 C. The gas constant R is equal to 8.31 JK to the -1 mole to the -1. This is 7 bad boy fat marks. All right, what I suggest is you grab a pen, a paper, your scientific calculator, pause the video, have a go at this question, and then unpause and watch the walkthrough. All right, let's get into it. So the first thing we've been asked to do is identify the limiting reagent. So when I'm looking at that, we need to work out the moles of our two reagents. And what are our two reagents? Well, we have our reactants here. We have magnesium, hydrochloric acid, and I'm going to want to do mass over MR gives me moles. So let's check it out. I've got 0.40 grams of magnesium, so I'm going to bust that out first of all. So I'm going to go 0.4 OOG, and I want to divide that by the MR of magnesium. Now, magnesium has an MR of 24.3. You can look that up on the periodic table. 0.44G. We're going to divide that by 24.3, and that is going to give me my moles of magnesium. And what does that equal? That equals 0.0165, 0.0165, and that's moles of magnesium. So let's just make that clear. That's Mg. Now let's work out our moles of hydrochloric acid. We've got 20 centimeter cubed of 1.5 mole per decimeter hydrochloric acid. So what we want to bust out here is this one. Of course, we used, just because my stuff deleted when I flipped to the periodic table there, won't be doing that again. That's the equation I used to work this out. I'm now going to use this equation to work out the HCl. So for HCl, let's type, because my writing is crusty, let's do 20 over 1,000. Why am I doing 20 over 1,000? Because 20 centimeter cubed here, us chemists, we like to use decimeters, so we're going to do 20 divided by 1,000. You could just do 0.02 if you prefer, and we're going to times that by 1.50. That's the concentration, that's mole, dm minus 3, and that is going to give us 0.03 moles. So at first glance, we're going to look and we're going to go, hey, dude, you've got 0.03 moles of HCl and you've got 0.0165 of magnesium. At first glance, it looks like I'm a twit because I've just done that. Can I delete this without deleting that? What? How does that work? Oh my days. Sometimes these things are amazing. So, oh my days, oh my days, oh my days. Right. At first glance, can I say at first glance anymore? At first glance, 0.03 moles of HCl looks like it's bigger than Mg, and it is. But does that make Mg the limiting reactant? Let's find out. We're going to look at the ratio of the reactants. So we've got Mg to HCl. We've got a ratio of 1 to 2. So the way to justify our answer here is to basically say, well, how much magnesium would I need to react with, how much HCl would I need to react with 0.0165 magnesium? Well, let's times that by 2. And if I times that by 2, I'm going to get 0.0165 times 2, bosh, that equals, I need 0.033 moles of HCl. So my justification is my limiting reactant is obviously HCl. I don't have enough. So my limiting reactant is HCl. The justification is I need 0.0165 moles times 2 equals 0.033 moles of HCl. I only have 0.03 moles of HCl. So we're short, right? We're short on HCl. So HCl is the limiting reaction, and there's my justification. Now, can you justify this in another way? Yes. What I could do is say I've got 0.03. I could divide that by 2 and say, look, 0.03 HCl will only use up 0.0150 of magnesium, which means we're going to be left with kind of 0.0015 moles of magnesium will be left over in excess. So magnesium's in excess. So you could kind of argue it a different way. Anyhow, this is going to get me, I would say, 3 marks. So 1 mark for working out the moles of magnesium, 1 mark for working out the moles of HCl. You've done the ratio, and then you're going to get a mark for identifying using the ratio that the HCl was the limiting reaction, and your mark for your justification. Now, what's the rest of it? We need to calculate the moles, meters cubed of hydrogen produced at 101 kPa and 15 degrees when R is 8.31. Let me get this out of the way. So what we're going to do, I'm going to do this working out here if I've got room. And what we're going to do is we're going to have to use PV equals nRT. So we're going to go PV equals nRT, and that's because we want to find volume, right? We need to calculate the volume. Luckily for us, this calculates the volume in meters cubed, so that's beautiful. We need to rearrange this to make V the subject. So I'm going to do nRT over P. So we're going to do this nRT divided by P, and that rearrangement is going to give us the volume. So now I just need to substitute all the numbers in. Now we've got 2 lots of moles. I've got these moles and I've got these moles, magnesium and hydrochloric acid. So which moles do I use? Well, the limiting reagent is HCl, so I need to use the HCl as my moles, because that one's going to get used up first. So the maximum hydrogen I can make is coming from the HCl. There's no hydrogen coming from the magnesium. So the maximum amount of hydrogen I can make is that, and the ratio is 2 to 1. So what I need to do to start off with, N equals 0.03. We're going to divide it by 2 because the ratio of hydrochloric acid to hydrogen is 2 to 1. And I'm going to end up with 0.03 divided by 2. Yes, I have to use a calculator because I'm simples. That gives me 0.015 moles. So I now know my moles are 0.015. What we're going to do now is go 0.015, that's my moles, and I'm going to times that by R, which is 8.31. And now I need to times that by T, which is the temperature, and the temperature is 15 degrees. However, in the ideal gas equation, we need to use this by adding to 273. So my temperature I need to put it into Kelvin. So we're going to add it to 273, and that's going to give me 298 K. Okay. Oh, are you with me? Now we want to divide it by the pressure. The pressure is in kilopascals. When you do the ideal gas equation, that needs to be converted into pascals. And you might say, oh, how do I have to know all these conversions? You just do. So you need to learn it. That's part of chemistry A level. So divide that by 101,000 pascals. And that is going to give us our answer. Whenever you do the ideal gas equation, PV equals nRT, there's going to be normally at least two conversions. So you need to double bubble check. You'll normally, if you get volume, say you're working out T, your volume is normally going to be given to you in centimeter cubed or decimeters, and you're going to have to convert it into meters cubed. So you need to know how to do your conversions. Your temperature is often in degrees, and you need to convert to Kelvin, and your pascals is often in kilopascals, and you need to times by 1,000 to put into pascals. Anyway, once we smash all of this into the calculator, we're going to get a small little number of meters cubed, and that is going to be 3.55 times 10 to the minus 4, 298, 288. See what happens when you don't use a calculator? Try to do it in my head, peeps. That's no good, is it? 15 plus 73. Who comes up with 298? I do. All right, guys, let's move on off of this question. So the answer is 0.015 times 8.31 times 288K divided by 101,000 pascals equals 3.55 times 10 to the minus 4. I tell you, what kind of Wally wrote 298? Right, let's move on. Let's zing down. So we're on to the last part of the question, and it says propane C3H8 undergoes complete combustion in a plentiful supply of oxygen. Give an equation for the complete combustion of propane. Use this equation to calculate the minimum volume in centimeter cubed of oxygen gas needed for the complete combustion of 50 centimeter cubed of propane gas. Assume that the volumes of both gases are measured at the same temperature and pressure. Equation for combustion. So the first bit is the equation for the combustion of propane. So we just want to do C3H8 plus oxygen. It tells us it's complete. So when you do complete combustion, you make carbon dioxide and water. And now it's a case of balancing. Balancing these organic reactions is nice and easy. We've got a 3 there for the C, so we just put a 3 there, 3 lots of carbon dioxide. We've got 8 H's. So what do I times H2 by? I times it by 4. 4H2 is 8. So that is always the case. Now we're going to go 3 times O2 is 6. 4 times O is 10. So 6 oxygens plus 4 oxygens is 10 oxygens. I need a 5 over here, and that gets me 1 mark. Now, because it says we are at room temperature and pressure somewhere, both gases are measured at same temperature and pressure, RTP normally. It doesn't matter if it's not at RTP. If you're at the same temp and pressure, then the volume of a gas is equal to the moles of the gas, essentially, as in like directly proportional to the moles of the gas. So the fact that I have 50 centimeters of propane, all I have to do here is, what does it actually ask me for? Assume the volumes, use this equation to work out the minimum volume of oxygen. Right. So I just need to times by 5. So I just need to do 50 times 5. Why? Because the ratio is 1 to 5 of propane to oxygen. And I'm going to get 250, right? Makes sense. Easy peasy, lemon squeezy. So the answer is 250 centimeter cubed. Dead easy peasy. And there we go. 9 beautiful marks. All right, guys. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Check out my other videos for A-level chemistry. I've actually got over 600 videos going on science. So let's get to it. Let's smash those exams. Okay, let's get into this next question. This is question 6. A student investigates the effect of changing the temperature on the rate of hydrolysis of 1 iota butane. The student follows this method, add 5 centimeter cubed of ethanol and 4 drops of 1 iota butane into a test tube. Mark this test tube with a cross below the level of the liquid. Add 5 centimeter cubed of 0.05 mole per decimeter silver nitrate solution to a separate tube. Place a stopper in both tubes. Place both tubes in a beaker of water at a known temperature between 5 and 60. Add After 5 minutes, pour the silver nitrate solution into the test tube containing 1 iodobutane and start a timer. Look through the transparent reaction mixture in the test tube towards the cross. Stop the timer when the cross is no longer visible due to the yellow precipitate formed. Identify the yellow precipitate. Okay, you can pause the video if you want to have a go here. Well, we've been told they've added silver nitrate here to iodobutane. They're kind of doing a disappearing cross experiment. You should know all your halide tests. So silver ions plus chloride ions make a white precipitate, silver plus bromide ions a cream precipitate, and silver with diiodine forming silver iodide is a solid yellow precipitate. Beautiful. That's going to get you a mark, nice and easy. Now we've got a question here. The student repeats the experiment at different temperatures. So they've done it at 6, 15, 28, 34, and 42 degrees. We've got time in seconds, and then we have 1 over T in the last column. So what do we have to do? Let's have a little looky down here. 6.2, plot the values of 1 over T against temperature on the grid. Let's just go up so you can see that properly. Draw a line of best fit. Use your graph to predict the time in seconds when the cross is no longer visible at 50 degrees, and that's 3 marks. Okay, so what we're going to do here, we're going to plot all these points on and just show you how I do that. So if we look at our table of results, the first thing I want to do is work out the scale, because it's always difficult plotting onto graphs. So if you're someone who finds it difficult, the first thing to do is work out the scale. Look for the value. 40 to 50 is 10. How many squares in between is 10? So I now know that for temperature, each mini little baby square equals 1 degree. Now, I want to plot on 6 degrees at 0.008. I need to work out the scale on my y-axis. So we've got 0.01 is the value, divided by 10. Each baby square is 0.001. Okay, now let's have a little look. So 6 degrees, I go along to 6 squares along, and then I go up to 0.008, and that is there. So basically 2 squares down from 0.01. That's my first plotted point. Let's look at the next plotted point, and you can see in the table the next plotted point is 15 degrees, and oh my gosh, I can't write, oh dear, 0.0120. Okay, that's some seriously bad writing. Okay, so I want to go across the 15. That's nice and easy, bang in the middle of 10 and 20, so easy to find. And you're going to go up and go 2 baby squares over 0.01 is 0.012. So that's the second point. Now remember, you can be half a baby square out and still get the mark. So we're now going to go 28 degrees, and 28 degrees at 0.02. So 28 degrees is 2 squares before 30, and we're going to go up to 0.02s, bang on that line. That's an easy one for us to do. Don't worry about the fact that the dots don't look evenly spaced. 34 degrees and 0.0263, just had to squeeze that in there. So we're going to go across the 34. That's 1 square before the mid between 30 and 40, so 1 square before 35, and then we're going to go up to 0.0263, so just over 1 square over the halfway line there. And then for the second last plot, that's at 42 degrees, and we're going 0.0385, so we want to go 2 squares past 40. We're going to go up to 0.0385. We're almost here, almost up at the last square below 0.04. That's all my plots. Now comes the difficult bit that I will screw up. I'm going to go in one steady line, very hard on the computer. I don't like the look of that. Now Okay, let me try that line again. There's orange. Ugh, not so good. But I do need to go all the way to the end, because what they're asking me to do is use your graph to predict the time when the cross is no longer visible at 50. It's quite smooth at the end, so maybe we'll go with that one. Smoother than the black line I did before. So we followed it through so we can make a prediction. I would have got 2 marks, one for the plots, one for the line of best fit. Now, oh my gosh, what am I doing? I'm changing the color. Let's not do it in green, Tommy boy. Let's stick with the orange. The orange is better. The orange is better. It's smooth at the end. That's what counts. So what I need to do now is use your graph to predict the time in seconds when the cross is no longer visible at 50 degrees. So I need to go along to 50 degrees, draw a line up on my graph. Now, the answer in the mark scheme will be different to your answer, because everybody's line is going to be slightly different, as we're all different abilities at drawing smooth lines. So I now draw a line across. excuse me, to the seconds on the y-axis, and I've got 0.054, 0.052, I reckon mine is. Each one of those is 0.001. Yeah, so mine is 0.052. You might look in the mark scheme, it says 0.054, but mine's not the mark scheme answer. So I will still get all 3 marks for this. So it's 1 divided by 0.052. We're going to do that, and that is going to give me the time in seconds, which is 19.23. So my 1 over t was 0.052, so my seconds is 19.23. And there you go. Now we're going to go to the last part of this, and that is 6.3. The student repeats the investigation using 1 iodobutane instead of using 1 bromobutane instead of 1 iodobutane. State and explain how the rate of reaction for 1 bromobutane compares with the rate for 1 iodobutane. Predict how the graph will differ for 1 bromobutane compared to 1 iodobutane. Right, how the rate, we get 3 marks here. How the rate of reaction, right, if I use 1 bromobutane, it's going to be slower. Now this is because the carbon-bromine bond has a higher bond enthalpy and therefore will require more energy to go in to break that bond. The carbon iodine bond actually has a lower bond enthalpy, so it's easier to break. Therefore, haloalkanes with a CI bond react faster than ones with a CBr bond. CBr react faster than ones with a CCl bond. CCl react faster than ones with a CF bond. And it's all to do with the amount of energy required to break the bond. As we go down the halides, we find that the bonds are easier to break. So the CBr bond has a higher bond enthalpy, so requires more energy to break. How the graph for 1 iodobutane will differ, it's going to be lower, isn't it? So it's going to be lower. It's going to take more time to reach the same point, but they're going to reach the same point eventually. So it's going to be lower, but finishing in the same point. And rather than draw it on the graph, we just need to explain it. Okay, welcome to Let's Get to the Marks, going through question 7. This question is about propanoic acid, CH3CH2COOH. This equation, the equation for the oxidation of propan-1-ol under reflux to form propanoic acid is shown. You can see we've got propan-1-ol, we've got an oxidation substance shown by the O in the brackets, and it forms propanoic acid. Notice that you always get a water molecule formed during this oxidation. Acidified potassium dichromate 6 is used as an oxidizing agent. State the color change in this reaction. Why don't you pause the video and have a go? Okay, I'm going to go through the answer. So potassium dichromate 6, the chromate ions are +6. Obviously, oxygen is -2. Times that by 7, you get -14. K, potassium is group 1, so +1, and that leaves you with 2 chromate ions that must be +6 to make 12 and cancel that out. Now, when it is oxidized and when you use it as an oxidizing agent, it's itself reduced. It gains electrons and it goes from green to orange. So your answer is green to orange. Okay, 7.2. A second organic product X is formed in small quantities. The boiling point of X is 49 degrees. That's quite a low boiling point. It's quite a volatile substance. This is something that evaporates easily. Identify X. Well, let's go up and look at what this small side product could be during this oxidation of propan-1-ol. So we're going to scroll up. And you look here, we got a primary alcohol. Why is this a primary alcohol? The OH group is attached to a carbon with 2 hydrogens attached. So this is a primary alcohol. And primary alcohols, when you oxidize them with potassium dichromate, if you're not refluxing, you're going to get an aldehyde. And then if you reflux, you're going to further oxidize them to a carboxylic acid. So we're looking at the oxidation to a carboxylic acid here. But of course, just because it's been under reflux, there will be very small quantities of the aldehyde. And which aldehyde will it be? Well, this is propan-1-ol, so it's propanol. And so we're going to get propan-1-al. Actually, no need to number it because aldehydes, the functional group always appears at the end of the molecule, unlike alcohols. So although you can get propan-1-ol or propan-2-ol, you can't get propan-2-al. You can only get propanal. Aldehydes, you don't need to number them. Their functional group only appears at the end of the chain. So the answer here is propanal. Now let's look at 7.3. Propanoic acid molecules cannot be separated from the reaction mixture by simple distillation because propanoic acid forms hydrogen bonds with water molecules. Complete the diagram to show how the propanoic acid molecule interacts with one water molecule through hydrogen bonding. Make sure you include in the diagram all the partial charges and lone pairs of electrons involved in this hydrogen bond, and this is worth 3 marks. So essentially we're getting a mark for showing the partial charges, a mark for the lone pairs, and a mark for the water molecule. And they just want one water molecule. So I'm going to draw my water molecule here, of course, OH2, so an O with two H's. Now I could bond from the hydrogen to the carboxylic acid, but I'm going to bond from the oxygen here. The hydrogen atoms will be delta positive. You don't really need to show that because they're not involved in the hydrogen bond with this one water molecule. But this delta negative oxygen is going to be involved. And it can't bond to the oxygen on the carbonyl group because that's also negative. They're going to repel. But it can bond to the hydrogen on the OH group on the alcohol because that's delta positive. So we're going to draw a dotted line to show that. And if I wanted, I could show another water molecule and I could do between the delta positive hydrogen and the delta negative O on the carbonyl group, or I could do between the delta negative O on the alcohol group there. But they asked for just one water molecule. So I'm going with the water molecule that's bonding to the OH on the carboxylic acid functional group. So I'm just going with this one. They specifically said one water molecule. Now, what have I missed out? I've missed out the lone pair of electrons. Now, there are two lone pairs of electrons on the oxygen molecule, and in the oxygen in both the OH group and the carbonyl group, there are two lones. But it's only one of those lones I need to draw the dotted line to. So I don't really need both of those lone pairs. You could just do one lone pair. It's one lone pair that is forming the hydrogen bond with that delta positive hydrogen. There are two lone pairs in the oxygen. You only need to show one. I showed two just to show you, but there we go. An alternative method for preparing propanoic acid is shown. So I've got bromoethane here, which is a halogenoalkane. And if you react it with sodium cyanide under reflux in a suitable solvent, it's going to form, what have we got there? Propan nitrile. So name and outline the mechanism for this step one. Name of the mechanism, let's go with that first of all. Well, if we look at the bromine atom, what's happened? It's been swapped with the nitrile group, with the CN. So what type of reaction do we call it when you swap something? That is a substitution reaction. Now, you can be forgiven if you made a mistake and thought it was addition, because notice it's gone from ethane to propane. It's gone, the chain has been extended, and extending the chain, people might think, oh, that's addition, but you've actually just swapped the Br for the Cn. So it's substitution. Now, what type of substitution? Well, the sodium cyanide is going to have a cyanide ion here, or a nitrile ion, whatever you want to call it, cyanide ion. And this is got a lone pair and a negative charge. Of course, that is going to be attracted to positive things like the delta positive carbon in the bromine carbon bond. So it's going to be nucleophilic. It's being attracted to the nucleophile, the delta positive carbon in that bond. So we call that nucleophilic substitution. Now we're going to get two more marks to outline the mechanism. So straight away, by the amount of marks, you know this is a simple mechanism. Nucleophilic substitution is a very simple AS level mechanism. It can come up in A2 chemistry as well. So what we're going to show here is the bromine carbon bond. Now, bromine is more electronegative than carbon, substantially more electronegative. So you're going to get delta negative on the bromine and delta positive on the carbon. That's going to mean that our nitrile ion, now I'm showing the three bonds here in the nitrile, you probably don't have to, you can just write Cn. You can put the negative charge anywhere on the nitrile, but that lone pair, draw the arrow from the lone pair to the delta positive carbon and then show bromine can only have one bond, carbon can only have four bonds. So we have to break that other bond, and that's going to get you the 2 marks for those 2 curly arrows. Make sure you've got the lone pair and the negative sign. You don't need to show the product here because that's going to pick you up all the marks for the mechanism. 7.5 suggests one reason why water is not a suitable solvent for step 1. So what we want to look at here is, why is water not a suitable solvent? Let's zing up. Okay, think about water. What kind of ions do we find in water? Well, water is H2O. Water is made of hydroxide ions and hydrogen ions, so OH minus. What's going to happen if your OH minus from the water, which also has a lone pair and a negative charge, is going to attack that delta positive carbon in the carbon bromine bond? Well, you're going to get nucleophilic substitution, but this time you're going to get hydroxide ion swapping for the bromine instead. So you're going to form an alcohol, you're going to form ethanol. So suggest one reason why it's not a suitable solvent. You could say because ethanol will be formed instead, or hydroxide ions form an alcohol via a nucleophilic substitution reaction where the hydroxide ion is attracted to the delta positive carbon in the carbon bromine bond. So essentially you're going to get ethanol, you might get an alcohol side chain. So this is the reason we are going with. Superbulous. Okay. Now we're looking at equilibria. A third way of making propanoic acid uses the reaction between ethene and steam and carbon monoxide in the presence of a catalyst. So we've got an ethene molecule plus a water molecule plus carbon monoxide. They're all gaseous, makes gaseous propanoic acid. It's exothermic, minus 59 kilojoule per mole. 7.6, give the expression for the equilibrium constant Kc for this reaction. So remember, we got products, we got reactants, and for Kc, Kc is equal to products over reactants. And so we're just going to write CH3, CH2, COOH, put the square brackets around that mean concentration. There's no coefficient, so we don't need to put any number in the top right corner outside the brackets. And we don't need to do that for the reactants either, as there's no coefficients in this equation. Basically, they're all just one molecule of each. So we've got C2H4, H2O, and CO underneath, all in square brackets, not round brackets. We're doing KC here. If it was KP, you round the brackets. You don't use square brackets. And that is going to get you a mark. Boom! Okay, let's zing down to 7.1. Table 3 shows the amount of each substance in an equilibrium mixture in a container of volume 1.2 decimeters at constant temperature. So I'm going to nick this. It says calculate Kc and state the unit. So I'm just going to use my equation that I had before. Save me having to write it out again, although you might need to. But you're not going to get an extra mark for that because that was already done. So all we want to do is substitute those numbers from that table in, and that's going to be your first out of 4 marks. So let's substitute the numbers in. So we're going to have products over reactants. So we're going to go 0.420. What we need to do is pay attention to the square brackets. What do the square brackets mean? Well, they mean concentration. Let's think of the equation, N over C times V. So if I want to find the concentration, I need to do moles over volume. They've given me the moles, the 0.420, but the volume is 1.2. So I need to divide 4.20 by, not naught, by 1.20. Which is the decimeter. So volumes in decimeters, I haven't got to convert from centimeters. So that is my concentration of propanoic acid. I need to do the same for the others. So I'm going to go 0.062 divided by 1.2 for the ethene. And then I'm going to go 0.078 divided by 1.2 for the water or the steam. And then I'm going to do carbon monoxide, which is 0.062. And I'm also dividing that by the volume, which is 1.2. Now I'm going to go ahead and mash that in the calculator and simplify these. So that's going to get you a mark. I'm going to simplify these so that I can get each one of these. If I try and put this all in my calculator with my skills, it'll all go wrong. So I end up with 0.3 over 0.0516 times 0.065 times 0.0516. Notice I put a little dot above the 6 because it's recurring. If you just do it like this without maintaining all of the long numbers, it was like 0.05166666667. If you don't put that in, you're going to get the wrong answer. So the right answer is somewhere between 2017 and 2020. If you just put it in like I have without putting more than 1.6 at the end of the 0.0516, you're going to get the wrong answer. You're going to get like 2022, and that will be outside the range given in the mark scheme. So they want you to retain those calculations on your calculator. So it is best if you can do it all in one go, but I've just tried to break it down a bit. Okay, now we're going to try and work out the units. For the fourth mark is for the units. So we've got mole dm minus 3 over mole dm minus 3 over mole dm minus 3 over mole dm minus 3. So you just write all the units out. You've got one thing on top, 3 things at the bottom of our Kc expression. So what we can do here is we can cancel out the mole dm minus 3 at the top and one of the ones at the bottom. And that leaves me with mole dm minus 3 and mole dm minus 3 at the bottom. I'm going to add them together. So you're going to get mole to the 2, dm to the minus 6. However, we're going to need to reverse it because there's a dividing line above them. So for whatever reason in maths, and I'm sure someone can leave something in the comments, when you have an empty dividing line above them, you reverse the symbol. So I just always add together my leftover mole to the dm minus 3s. And then if there's a dividing line above, I reverse the symbols. If we're above the dividing line, then I don't reverse the symbol. So mole to the minus 2, this will be dm to the 6. Notice I've reversed those symbols. So the minus goes to the 2 and the 6 becomes positive. So mole to the minus 2, dm to the 6, that is the units. And that's the end of that question. All right, but it's not the end of the whole of question 7. That's just the end of that little bit there, because we've got another one, 7.8. Predict the effect of increasing the temperature on the yield of propanoic acid. Explain your answer. It's 3 marks. Of course, pause the video, have a go. Should do that with all of these. You're going to get 1 mark for describing the effect on the yield and 2 marks for the scientific explanation. Let's go up and find out. So when we look at the equation, we can see that the delta H is minus 59. This is an exothermic reaction. And when you're looking at temperature, you need to identify if it's an exothermic or endothermic. And on the right-hand side is what we call the reaction. So the right-hand side is exothermic. If you make the temperature higher, that's the hot side of the reaction. The endothermic side, the left-hand side, is the cold side of the reaction. Le Chatelier's principle said, look, if you change the conditions of a reversible reaction in equilibrium, it is going to shift the position of equilibrium to the side to oppose the change. And that means this reaction is going to shift to the left, the cold side. You're increasing the temp, it's going to try and oppose you and decrease the temp and make it cold. So we're going to get a decrease in the yield of propanoic acid. That's going to go down. And the reason is it's an exothermic reaction, and that will get you a mark. But we want the full 3 marks. So we want to say, the equilibrium position will shift to oppose the changing conditions. So because you increase the temperature, the equilibrium position will shift to the left or in the reverse direction or the endothermic side of the reaction in order to oppose the increase in temperature. It wants to absorb that heat energy, therefore try and reduce the temperature back to what it was before. And there we go. That's the end of the question. Don't forget sharing's caring. Hit the like button. Through the MCQ for the 2024 Paper 2 AS Chemistry AQA. Don't forget to pause the video at the start of each question and have a go, and then unpause and watch each question's explanation. Question 8. The equation shows how P reacts with Q to make R and S. P plus 2Q goes to R plus S when a mixture of 0.25 mole of P and 0.4 moles of Q react. 0.15 mole of R is obtained. What is the percentage yield of R in this reaction? Hopefully you know the equation. Percentage yield is actual mass over theoretical mass, or we could do actual moles over theoretical moles times 100. Now what we want to do is find out what's the limiting reactant, because you use the limiting reactant to work out how much product you should make. So I've got 0.25 of P, but it's in a 1-to-2 relationship with Q, which means I should have 0.50 of Q, but I don't. I've only got 0.40 of Q. Therefore, Q is limiting, and I'm going to use that to work out how much product we're going to make. You always use your limiting reactant to find out the maximum product. So as it's in a 2-to-1 relationship with R, and I have 0.4 of Q, that means the maximum amount of R I can make is 0.20 moles. So if I can maximum 0.20 moles, because it's a 2-to-1 relationship, it means the max moles is 0.2. The actual moles was 0.15. So I want to do 0.15 divided by 0.2 times 100. That gives me my percentage yield. No, it's not D. It's going to be A, because it's 0.15 over 0.2. There we go. Boom! What is the MR of this compound? Question 9. Pause the video, have a go. Okay, it's skeletal formula. I'm going to turn it to displayed. So put my methyl groups at the end of those lines, put carbons wherever there's a point on this kind of formula, and then write in the hydrogen atoms. Make sure you've only got 4 lines around each carbon. So that gives me 4 carbons, right? 8 hydrogens and 1 oxygen. Hold on a minute. No, not 4 carbons. You don't. Oh, 6 carbons. So we want to go 6 times 12 is 72, plus 8 for the single hydrogens, plus 16 for the oxygen, makes an MR of 96. That'll be B. Thank you very much. Right, let's move on to question 10. Which statement explains why the rate of reaction increases when a catalyst is added to a reaction mixture at a constant temperature, and it's worth 1 mark? Right, what I'm going to do for this one is draw out the Maxwell-Boltzmann distribution. So hopefully you know that. You got your Y, you got your X, you got your number of particles on the Y, you got your energy at the bottom of X. Then we've got a camel's hump. So you just draw like a camel's hump going across here. And then we're going to put our activation energy, and it's beyond the activation energy to the right-hand side of a line that I'm going to put here. That's a bit close to the end. Probably shouldn't be there, but never mind. I'm going to call it AE, activation energy. From the right-hand side of that line, those are the particles with enough energy to successfully collide. If you use a catalyst, the activation energy shifts to the left, it decreases. So EAC, energy of activation, catalyst, whatever, which means we're going to have a higher proportion of successful collisions because we've decreased the activation energy. So it's going to be C. You haven't changed the size of the camel's hump by adding a catalyst. So you haven't changed the mean energy by doing that, and you haven't increased the activation energy, which would shift it to the right and make it a lot slower. Right, let's move on to question 11. Which labeled curly arrow shows an incorrect movement of an electron pair? So we're looking at a pair of electrons moving from something to a bond, and let's look which one is incorrect. These ones are always tricky. Let's look at A. Well, we've got the pair of electrons on the hydroxide ion going to the hydrogen. That looks good. And then from that bond going to the bromine. Yeah, they're both good. So we can get rid of A and B. Then we got this pair going to this bond, which would happen. It's got to split off. Oxygen can't have 3 bonds. Oxonium ion, get rid of that. And then over here, well, really, that lone pair is going to want to. You've got that carbocation there. We've got that positive, so that is going to need to have electrons go to it, whether from the that water molecule with a lone pair, or whether from one of the bonds. But that's going to be the case. Oh, this is one dirty one. I'm going to leave this. I'm going to put a star here. This question is so long that I reckon this is a 50-50 one. This will take you about 3 or 4 minutes, maybe 10 minutes to actually work out going through carefully. So I'm going to leave that right to the end and see if we have time. Bit of exam technique there. Right, which diagram shows the correct apparatus for the conversion of hexan-1-ol to hexanal? Hexan-1-ol is a primary alcohol. Hexanal is an aldehyde. Which of these would you use to make an aldehyde? Why don't you pause the video, have a go. I know I've shrunk it down. I've tried to get the whole question in. Okay, so we've got a primary alcohol there, OH group attached to a carbon with 2 hydrogens, going to make an aldehyde, it's going to make hexanal. You don't get a number with hexanal because aldehydes, the functional group's at the end, so we don't number it. We're going to need distillation. If you reflux a primary alcohol, it will go straight past aldehyde, oxidize to aldehyde, oxidize again to carboxylic acid. So if you look at the diagrams for C and D, they've got the pear-shaped flask and the condenser vertical. They are reflux diagrams. Get rid of C and D. Beep, beep. So the answer is A or B. And what we're going to notice is the only difference is where the water goes in and the water goes out. Now, B is the correct answer because in distillation, water should always come in from a lower point and move up to a higher point against gravity. This ensures that the condenser will be completely filled with cold water, and it will ensure maximum efficiency of energy transfer between the vapors inside the condenser and the water inside the walls of the condenser, and you're going to get the maximum condensation. So B is the correct answer. A is the incorrect way to set up a Liebig condenser. Okay, let's move on. Okay, question 14. Let's zoom in a bit. 1,1-dichloroethane Y reacts with chlorine to form hexachloroethane Z. Which is the correct equation for this reaction? So going to write out the formula for 1,1-dichloroethane here. I'm not going to put the H's on because I can't be bothered. C2H4Cl2 would be the formula. I'm going to add some chlorine to it. And what am I going to make? I'm going to make C2Cl6 because the 4 H's will be swapped for chlorine. So it'll be C2Cl6. But what's going to happen to the 4 hydrogens? Well, they're going to form HCl, hydrogen chloride. And I'm going to need to write HCl, and I need 4 of them because I've got 4 hydrogens in my original 1,1-dichloroethane, so I have to make 4 hydrogen chlorides because we need to balance up the hydrogen. So I'm going to put 4 in front of HCl here, and then we need to add up the total amount of chlorines on the right. I mean, we already know which one it is now, but we can add up the total amount of chlorines on the right hand side, and we find we've got 10, we've got 6 in the new product, and we've got 4 with the HCl, which means I need 10 on the left hand side, so I need a 4 in front of Cl2. The answer is B. Boom. Right. Let's go. 15. Which is the structure of poly-1-chloropropene? So, okay, monomers always have a double bond, and what you got to think about is when you get rid of a double bond and you turn it into a polymer, you should draw open-ended brackets at each end. Okay, I haven't put all the hydrogens on here, I can't be bothered, but you must leave open brackets at the end like this, and so we can get rid of C and D because they've got 3 carbons in the middle. The only carbons in the middle of your brackets should be the 2 carbons that had the double bond. So now we're looking at A and B, And this told us to do 1 chloropropene. And if it was B, that would be 2 chloropropene because the chlorine is on the middle carbon of 3. So the answer is A. Right, 16. Octadecane is a straight chain alkane containing 18 carbon atoms per molecule. It's cracked to produce oct-1-ene and 2 other compounds. Which equation represents this reaction? Pause the video. Have a go. All right. Alkanes, think about them. CnH2n plus 2. So we've got octadecane. Tells us it's got C18. Why am I writing C8, you idiot? Right. It's C. So I want to do this C2. C18 times 2 add 2, right? So times 2 is 36, add 2 is 38. Right. So I'm looking for any with that. And straight away, look at this first one, A, C6H36. Get rid of that. That's wrong. All the others could be right. They've all got C18H38. But what does it say they make? So it says they produce oct-1-ene. Oct-1-ene. Now, oct-1-ene is going to be an alkene, and they have the formula CnH2n. So I'm looking for something which is going to be C8H16. And I've got C8H18. That's octane, not octene. So that's wrong. And then down here, I've got C8H18. Again, that's octane. That's times 2, add 2. That's an alkane, not octene. Octene's going to be the one above with C8H16. So it's going to be B, because that makes the right product. Oct-1-ene, C8H16. There we go. Okay, 17. Which of these alkanes has the highest boiling point? Okay, so let's go through and work out their boiling points. So let's compare decane and hexane, A and B. So decane's larger, right? 10 carbons, hexane 6 carbons. So decane is going to have more van der Waals forces. What's that? WDV? Oh, I can't even work out how to say van der Waals forces. But van der Waals? Yeah, whatever. It's got more van der Waals, more intermolecular forces. 2,3-dimethyl octane. Octane's bigger than butane. So again, C is going to have a higher boiling point than D. So now we're just comparing A and C. We want to know which one has the higher boiling point. Well, decane is a straight chain, and 2,3-dimethyl octane is a branched chain. Now, the issue we have here is straight chains always have a higher boiling point if they have a similar MR to a branch chain one. The reason is they can approach each other closely. They don't have branches to get in the way, and so there is stronger intermolecular forces. 18. High-resolution mass spectrometry can be used to determine the precise relative molecular mass of compounds. Which compound has a precise relative molecular mass that's different from the precise relative molecular mass of butanone? So when we look at butanone, it has the same molecular formula as these others. So we're really looking for one with a slightly different structure. And so what we find here is it's C4H8O. That's 72 as the MR. Let's write this out. But3N1-ol is going to have an OH group on the end. It's going to have a double bond on the third carbon. Yeah, it's still C4H8O. It's going to have a very similar precise molecular formula. Not only is its molecular formula the same, but its molecular mass is going to be very similar. If we look at cyclobutanol, this is going to be C4H8O once again. And then if we look at methyl propanol, that as well is going to be C4H8O. Oh my good gosh, let's look at prop-2-enoic acid. And what we're going to find here, it has a different molecular formula. Although the MR is the same or similar, has a different molecular formula. So its precise MR molecular mass is going to be different because it has a different molecular formula. And so that affects the precise relative molecular mass. Its formula is C3H4O2. There we go. Right, let's use this information to answer questions 19 and 20. So we got a whole heap of information here. And what we're going to do is we're going to solve what is the enthalpy of combustion in kilojoules per mole of propane. And so what I need to do is flick up to the table, study the data, and then write some sort of Hess's law enthalpy cycle. Let's get to it. Okay, so what I want to do here is we're asked to work out the combustion of propane. So I'm going to write the propane combustion kind of thing. I should really write C3H8 plus O2. You're not going to combust without the O2, but I can't be bothered. So this is the enthalpy of combustion, and we've got carbon dioxide and water on the right-hand side. Now, when propane combusts, we don't know what that is yet. But what I do know is to form carbon dioxide and water. I'm drawing two arrows going up from hydrogen, oxygen, and carbon at the bottom, I should write. And I'm going to need to form 3 molecules of carbon dioxide and 4 molecules of water, because that is going to be their ratio in a balanced equation of combustion. And that makes a total of minus 2,323.7 if we add up the total enthalpy change for the formation of water. 3 moles of carbon dioxide and 4 moles of water is going to make minus 2,323.7. Now, I need to write down the formation for propane. Have we been given the formation of propane from its constituent elements in their standard conditions? Yes, we have. It is minus 104. I'm going to write the elements now: carbon, hydrogen, and oxygen. I should have oxygen on the left-hand side at the top there, but I didn't bother. So that is minus 104. I now draw my red arrow going all the way around, and wherever the arrows are in alignment, I keep that sign the same. So the minus 232.7 is in alignment, but the minus 104 goes against my red arrow. So I reverse it and make it plus 104 minus 2323.7, and I get an answer of minus 2219.7. And the closest answer to that is C, and that is the correct answer. So it's just doing a Hess's law cycle. Right. What is the enthalpy change in kilojoule per mole when butane reacts to form propane, hydrogen, and carbon? Jeez Louise, this can be a bit difficult because I'm going to have to swing up and swing down. So if you might want to write those numbers down and then pause the video and have a go. All right, I'm going to go through the answers. So we're going to have C3H8 and no, sorry, scribble that out. I'm doing propane, so C4H10, and that's going to form C3H8 plus H2 plus carbon, and that's all balanced, right? One C4H10 breaks down into a C3H8, an H2, and a carbon. So I have combustion data. Do I have data for these? No, I've got, if I reverse the formation data, so if we go from butane downwards, these are the numbers. So I'm going to go from C4H10 down, and that's going to give me plus 125.2, and that's going to form carbon, hydrogen. And if I go from propane down, that's going to form plus 104. And hydrogen and carbon are in their elemental state, so we don't need to worry about that. They have 0 on the enthalpy change. I'm going to do the same thing, draw the arrow going around, and reverse it when the signs are against each other. And I'm going to reverse the 104 again because its sign is against. So it's plus 125.2 minus 104. Bosh, 21.2. And it's positive, not negative, because no minus came up on the calculator. And there you go. The answer is A. Don't forget to leave a comment if there's any questions you're unsure about. 21. This is an equation for the conversion of 1,2-dibromo ethane to butane dinitrile. What's the percentage atom economy? So what we're going to do here, pause the video, have a go with a pen and paper, etc., is we're going to use atom economy, and you're basically useful product over total MR of the products. So it's kind of useful products over total products. You could do it as mass or whatever. So what we're going to do here is the useful product is this over here. The products are on the right. So I've got 80 there is my useful. And underneath I want 2 times 119, which represents 2 kBr, and 80 and times 100, the whole lot. And that's going to give me 25.2%. Now, 22, last question in the exam, a sample of cyclohexane contains 3.011 times 10 to the 20 4 atoms of carbon. What is the mass of this sample? Avogadro's constant, known as L, is 6.022 times 10 to the 23. So we've got a couple of equations to consider here. Mass is equal to moles times mR. We want mass. So we're going to need to do moles times mR, something times 12. Let's work out the moles. We can work it out from the Avogadro's equation. If you don't know it, its number of particles is moles times Avogadro. So I can rearrange that and go, well, I know the number of particles is 3.011 times 10 to the 24, and I know Avogadro's, and if I rearrange that, I can make moles the subject, divide both sides by Avogadro's, and I'll get 3.011 times 10 to the 24 divided by 6.022 times 10 to the 23. So I'm rearranging this equation, and this is going to give me the number of moles, which is 5. Okay, so there are 5 moles of carbon atoms. Now, we know the MR of carbon is 12, so I can do moles times MR equals mass, 5 times 12. The mass of carbon is 60. And then I look over here at the answers A, B, C, and D, and none of them are 60. Why is that? Because the question, if we read it carefully, said what is the mass of the sample? So we've got to include the hydrogen. Cyclohexane is made of carbon and hydrogen. Cycloalkanes have the same formula as alkenes. So cyclohexane, why have I put C12? You buck. It's going to be C6. Oh my gosh, C6H12. So they've got the same formula, CnH2n. So what's the ratio of moles of, what's the ratio of moles of carbon to moles of hydrogen in cyclohexane? Well, the ratio is that for every mole of carbon, you have 2 moles of hydrogen. Now, as I had 5 moles of carbon, that means I've got 10 moles of hydrogen. And so we need to work out 10 moles of hydrogen. Hydrogen has an MR of 1, so it's going to be 10 times 1, and that is going to mean hydrogen atoms have 1, so I've got an extra 10 grams, so 60 plus 10, I'm looking at 70 grams for the total mass of this sample. Lovely bubbly. Okay, now going on to that one that I starred earlier, really, really difficult. With this one, you basically need to prove which of these can form those 5 alkenes above. I'm just going to go through the correct answer. I've gone through this before loads of times. This takes about 15 minutes to go through, and I don't have that kind of time in my life, I'm afraid. So I'm going to go through the correct answer. 3-bromo, 3-methyl hexane. So I'm going to draw out this 3-bromo, 3-methyl-hexane and show why it can make all of those. And if you do the others, some of them can't make EZ because you end up with the same group on the same carbon atom in a double bond. So you can't get EZ isomers when you get that. And some of them can't make the 2-ethyl pent 1-ene, but to go through each of them is just painful, drawing out display formulas and trying to show how it all works. Anyway, what I'm doing here, this is 3-bromo, it's on the 3rd carbon, and 3-methyl on the 3rd carbon hexane, right? I'm going to have a hydroxide attack, and you're going to get elimination, not substitution, when you have ethanolic hydroxide. So it's going to attack a hydrogen always on the adjacent carbon to the carbon with the halogen. So it's going to attack either that hydrogen or the hydrogen on the other side or the hydrogen on the methyl group. Now, if it attacks this hydrogen on the one on the other side of the bromine, we're going to get a double bond formed there. The bromine's going to break off. The hydrogen above it's going to break off. And what are we going to end up with? Well, we're going to end up with, that's going to give us hex-2-ene, right? This is going to give us hex-2-ene because we're going to get a double bond here. And that could potentially be hex-2-ene, and it's going to be 3-methyl-hex-2-ene. And so that gives us either E3-methyl-hex-2-ene or Z3-methyl-hex-2-ene. And why is that? Well, we've got a methyl group here. I've got a propyl group here. I've got a methyl group on that carbon and a hydrogen. So on the first carbon, I have a methyl and a hydrogen attached. They're 2 different groups. On the second carbon, I have a methyl and a propyl group attached. They're 2 different groups, so we can have EZ isomers, and this is hex-2-ene. So I'm just showing you that it's possible to get E3-methyl-hex-2-ene or Z3-methyl-hex-2-ene. Now let's look at the possibility. Can we get E3-methyl-hex-3-ene, and can we get Z3-methyl-hex-3-ene? Well, you're damn right we can. All that has to happen there is the bromine, and I'm going to rub this out, hold on. All we need there, I can't be bothered to do it all again. All we need there is the double bond to form there, okay? And it would form there, and then what we would have the same kind of thing. We'd have an ethyl and a methyl and a hydrogen and an ethyl on the other side, and that would be methyl-hex-3-ene. So we can get that too. Now what I want to do is just show you, the last one is to show you how we can get ethyl 2-ether pent 1-ene, and to show you how we get 2-ethyl pent 1-ene. Oh my good gosh. Let's redraw. Jeez Louise, this, you see why I'm just doing the correct answer. If I was to go through each of the incorrect answers, which I started to do when I was doing this, and I was like, oh, this is just too long. So what's going to happen here? The hydroxide this time attacks a hydrogen on the methyl group that's adjacent to the carbon with the bromine on. So it's still an adjacent carbon, and it's attacking that. So what's going to happen? The double bond is going to form there. The bromine's still going to break off. And we're going to be left here now with this looking molecule. The double bond's going to be here. And we're going to number this as pence, right? So we want to number that 1, 2, 3, 4, 5. But if I number it this way, no. Sorry, I've got to number it the other way because that wouldn't make sense. Right. Let's number it this way. 1, 2, 3, 4, 5. So that's pent-1-ene, right? The double bond is on the first carbon, so pent-1-ene. And then where is the ethyl group? 2 ethyl pent-1-ene. So that's how we get that one as well. So these are all part of your elimination. Now, the reason I said I leave it to the end is because with difficult ones like that, you might run out of time. At least then you're guessing with that kind of one. So remember, the last thing you want to do is get to the end and you've got an easy one like work out the MR and you've run out of time and you're like, oh my God, that was a mark in the bag. Whereas this one is quite tricky. All right, guys, I hope that helps. Don't forget sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. I'll see you on the next vid.
You're still here? It's over.